We shift gears. We move to problem 3 and problem 4 of the 2025 MIT Integration B finals. That will be number 3, which is a definite integral from x equals to 0 to x equals to 10 of the flow of the flow of x power of 1 plus the square root of 5 over 2. Okay, that's very interesting. And then the problem number 4, which is also indefinite integral from x equals to 0 to x equals to pi of the product of the square of a maximum between the absolute value of 2 sine x and the absolute value of 2 cosine x minus 1, and the square of the minima between the absolute value of sine of 2x and the absolute value of cosine 3x. So certainly these are all very interesting problems. We are going to take time and break them down in a way that is easy to understand. If you have a question and you have an area that you don't understand, we do welcome you to reach out to us via the comment section, or you can email to us directly. We would love to hear from you. If you have an alternate method of working on these problems, also would love to know it. So without much ado, let's jump into the solutions to these problems. So I think the first thing for us is to really understand what the flow function is all about. That is, if let's say we have a flow function or a flow of a function f(x), that is equals to k when the value of f(x) lies between, or it's greater or equal to k and less than k plus 1. So what that means is that this is the integer value of any function such that when f(x) is between k and k plus 1, f(x) will take the integer value immediately less than that function value. Okay, so in this situation here, we have x, and that means that between 0 and 1, x will be 0. Between x and 1 and 2, x will be 1. And that means that now we've discretized this integration into strips. So there is k equals to 0. In that event, we're integrating from k or from 0 to 1, and that is from k to k plus 1. And that goes all the way up to 9, because from 9 to 10, 10 is our limit. The entire value of flow of x is going to be k, which is equals to 9. And so that's what our problem has become. Now we can now go ahead and say, okay, this is a constant, right? So in other words, we're just going to integrate 1. We pull that constant out. And that means that now we have the x with limit k and k plus 1. So k plus 1 minus k is just going to be equal to 1. And so our actual problem now is going to be equal to just summing up the flow of the kth power of 1 plus root 5 over 2 from k equals to 0 to k equals to 9. Okay, so this is our problem. And that's interesting because now we can go ahead and say, okay, what is 1 plus root 5 over 2, so that when we power it, we get what we want, right? So let's assume that x is equals to 1 plus root 5 over 2, and that means that 2x is equals to 1 plus root 5. That also means that when we pull 1 onto the left-hand side, we now have 2x minus 1 is equals to root 5. So when we square both left and right-hand side, we have 4x squared minus 4x plus 1 on the left hand side equals to 5. So subtract 1 from both sides, we have 4x squared minus 4x equals to 4. So when we divide across by 4, we're going to get x squared minus 1 equals to x squared minus x equals to 1. And when you add both sides with x, you get x squared equals to x plus 1. So this is very important. This is very important, and we're going just to hold it for now. The next thing is we want to know what x is, the approximate value of root 5. As the same as 4 plus 1, and then the square root sign, and then we can pull 4 out so that we have 2 times 1 plus a quarter. And now we can look at the expansion of 1 plus x to the power n. That's the same as 1 plus nx plus n times n minus 1 over 2 factorial times x squared, and so on and so on and so on. So this is important, how you could arrive at this. You could use Taylor's expansion, or just the binomial expansion of this would lead to this. Anyway, so if we have a half in place of n, so we have 1 plus a half x plus a half times a half minus 1 over 2 factorial x squared. And since our root 5 is the same as 2 times square root of 1 plus a quarter, the same as 2 plus a quarter to the power 2, which is 2 plus, using this formula, a half. In place of x, we have a quarter, and that can quickly expand to what we have here. And this is important. It's easy to see that, okay, a half times a quarter is 1 over 8, and here we have negative quarter divided by 2, which is negative 8 times 16, so we have negative 1 over 256. And so you can add up, and we have 2.234 as our approximate value for the square root of 5. So now x being 1 plus root 5 over 2 is approximately equal to 1 plus 2.234 over 2, which is just 1.62 approximately. So that now we go and say, okay, when k equals to 0, x to the power 0 is that whatever is in the bracket to the power 0, which is 1. When k equals to 1, the same as x to the power 1, which is 1 plus root 5 over 2, the power 1, which is the same as 1.62. When k equals to 2, that means that we have x squared is equal to x plus 1. We're just adding 1 to that, and so we can also check that when k equals to 3, x to the power 3 is equal to x squared plus x, multiplying x on this. Just multiply x here, we get x to the power 3, multiply x here, we have x squared, multiply x here, we have x. And so x to the power 3 is the same as x squared plus x, and x squared is the same as x plus 1, so we substitute x plus 1. So x cubed is the same as 2x plus 1, and we can just feed in 1.62, and we get 4.24. When k equals to 4, multiply x on both sides here, actually both sides here, so we get 2x squared plus x, and so we eventually get 3x plus 2. Do multiplication, 5.86. And k equals to 5, x to the power 5 is the same as we multiply x on both sides here, so we have 3x squared plus 2x. In place of x squared, we just put x plus 1, and that leads to 5x plus 3. And we can substitute 1.62 in place of x, and so we get 11.10. Next, k equals to 6, the same thing, and then we get 17.96. When k equals to 7, we do the same thing, and we get 29.06. And then when k equals to 9, we do the same thing, and we come to 34x plus 21. We substitute 1.62 in place of x, and we get 76.08. Such that now if we have all these values, the flow function summation becomes the floor of 1, the floor of 1.62, the floor of 2.62, the floor of 4.24, the floor of 5.86, the floor of 11.10, floor of 17.96, the floor of 29.06, floor of 47.02, the floor of 76.08. Here we'll get 1, and here is 1. So we're just adding 1 plus 1 plus 2 plus 4 plus 5 plus 11 plus 17 plus 29 plus 47 plus 76. And that adds up to 1.93. I mean, sorry, 193, not 1.93. So 193 is the summation we get here. So that's just the quick thing. I think the important part is in getting the approximation of the square root of 5. You have to get it really nicely to a point where if you substitute into the succeeding powers, the values that correspond to succeeding powers of x, you get the right values, so that when you get the floor function, it gives you the right value. So this is certainly a test of one's ability to do the multiplication and approximation, but all the same, an interesting problem. I hope you like it. So on to this problem number 4, where you have an integral of the product of the square of a maximum between the absolute value of 2 sine x, 2 cosine x minus 1, and the square of the minimum of the absolute value of sine 2x and cosine 3x. So this is a very interesting problem, and that's from 0 to x equals to pi. I think when somebody looks at this problem, the quick temptation for them is to rush in and try to plot out and see where sine 2x, I mean 2 sine x is maximum over is greater than 2 cosine x and so on. But it's actually easier to just wait and see what the minimum function here entails. So let's try to expand the sine 2x, because there's a relationship here between sine 2x here and sine x. So let's try to expand that out so that we see what's really happening. Okay, I have color coded the minimum part as blue just to highlight what we're going to be focusing for now. So let's just focus on the blue part. So sine 2x, let's begin with cosine 3x. Cosine 3x is the same as cosine 2x plus x, right? And so using cosine a plus b equals to cosine a cosine b minus sine a sine b. So here we are having, we're going to have cosine 2x cosine x minus sine 2x sine x. Okay, so when that happens, and that's just going to happen in this next line here, so we have, in place of cosine 2x plus x, we have cosine 2x cosine x minus sine 2x sine x. So let's expand the sine 2x part there, and sine 2x is the same as 2 sine x cosine x, and that allows us to now write, we want to express this cosine 2x, we want to get a cosine 2x on this other side as well. So we have 2 cosine x sine x, and when we multiply sine x and sine x, that becomes sine squared x. So we have sine squared x, expressing sine squared x in form of cosine 2x. That means that this 2 and sine squared x is the same as 1 minus cosine 2x. So we're going to write 1 minus cosine 2x there, right? And so we can bunch this and this, and we get 2 cosine x minus cosine x. Okay, so that's what we've done here. And we can now go ahead and pull out the cosine x bit. Also, we should express sine 2x as 2 sine x cosine x. That's what we've done here. And what we see here, we have cosine x, that is a factor here, and we have cosine x, that's a factor here. We've pulled the cosine x and this cosine x out, so we have 2 cosine 2x minus 1. So since this is common, we can pull that out and focus on the minimum between 2 sine x and 2 cosine x minus 1. And already you see, let's probably pull that out fast so that it's easy to visualize. Okay, this is kind of interesting, right? Makes the problem really cool. So we've pulled out a factor, and that is, for example, if you're being asked what is the maximum or the minimum between 4 and 2, right? You could pull 2 as a factor out, so that now you're looking at what is the maximum minimum between 2 and 1. And so that's what we've done here. We've pulled out that factor, which is cosine x absolute, right? And there's a square. And so now we're looking at what is the minimum between 2 sine x and 2 cosine x minus 1. And you see that whatever is inside this maximum and minimum factor, they're all the same. They look the same. So it doesn't really matter now, because if we're getting the maximum here, then evidently the other part is going to be the minimum. And so for any region where we're looking at the maximum and minimum, it's just going to be the product, the square of the product, the product of the square of these functions. And that's what we're going to do. So we're just going to say this is the same as the product between the square of the absolute value of 2 sine x and the square of 2 cosine x minus 1 absolute times the square of cosine x absolute. And even these absolute values kind of vanish, because now if you're looking at the square, it's just it means they're all positive at all those points. So we're just going to look at the product of the square of actually 4 sine squared x, the square of 2 cosine 2x minus 1, and the square of cosine x. And that's, we can even simplify this further, because now we can bunch the sine squared x and the cosine squared x, so that now we have 2 sine x cosine x, which is the same as sine 2x, right? So now that we have sine squared 2x, we can pull the sine squared 2x inside the bracket here, so that now inside the bracket we have 2 cosine 2x times sine 2x minus sine x. Okay, this is the same as sine 4x, right? Because yeah, this is sine 4x. When we square that, we get the integral of the sine of the square of sine 4x minus 2 sine 4x sine 2x plus sine squared 2x. Okay, so that's what we have for now. So now that we do have sine squared 4x minus sine 4x, 2 sine 4x sine 2x plus sine squared 2x, we can express this as a double angle expression. So sine squared 4x minus sine 2x is the same as 1 minus cosine 8x over 2, and this here is the same as cosine 2x minus cosine 4x, and this here is the same as 1 minus cosine 4x over 2. And so we can get this half and bunch with this half. This is going to be 1, and then we see here this is plus cosine 4x minus sine 4x over 2, so that's going to be a half. So just bunch that. We have 1 minus cosine 2x minus cosine half cosine 4x plus cosine 8x. So this cosine 2x comes here, and this cosine 8x comes here. Because there's a minus here, it becomes plus. These are pluses, but because this is a plus here, there's a minus here. And when we integrate these respective cosine terms, they become sine, and any integer multiple of pi under the cosine function is going to be 0. Same as 0. So this entire part, when integrated, just collapses to 0. But this part here persists, and that becomes pi. So that's the answer that was being sought. Certainly a very interesting problem. I hope you like how we've arrived at the answer. So until next time, hope you subscribe to our channel if you haven't. Like if you've not liked, share if you feel inclined to share. It was an absolute pleasure solving this problem. We're still left with one more problem, and then we round up the 2025 MIT Integration B. But yeah, please subscribe to our channel if you have not subscribed. We'll really love your support on this. We do love mathematics, yet everyday mathematics, and we hope you share with us in this journey.